Fan systems improving system efficiency. Welcome to our session on fan systems, improving system efficiency. Today, we'll dive into 3 critical areas that can optimize fan system performance. We'll discuss major opportunities for improvement, identify common issues, and look at methods for controlling airflow in various fan systems. By the end of the session, you'll have actionable insights to apply in your operations. Let's get started. Topics to be covered. Define the main opportunities to improve performance in fan systems. List common fan system problems. List the ways that airflow is controlled in fan systems. Industrial fan. Industrial fans are built for different purposes, with designs to meet specific airflow and pressure requirements. These fans must be chosen based on their intended application, considering factors like air volume, static pressure, and efficiency. Using the wrong fan type or size can lead to inefficiency and high energy use. Selecting the correct fan type from the start can ensure long-term reliability and reduce operating costs. Let's move to some fan configurations to see how different setups can impact performance. AC fan and motor. AC fans paired with suitable motors are the workhorses in most industrial settings. The key to optimizing them is matching motor capacity to fan demands, so the motor doesn't run harder than necessary. Oversized or undersized motors can lead to energy waste and unnecessary wear. Regular maintenance, like checking for worn bearings or loose connections, is also essential to avoid performance issues. This foundational setup, when properly managed, provides consistent, reliable airflow in various applications. Direct drive fan. Direct drive fans are simple, efficient, and low maintenance because they eliminate belts and pulleys. This configuration directly connects the fan blades to the motor, reducing energy loss and removing the risk of belt slippage. Direct drive fans are ideal for high-efficiency environments where space is limited and maintenance needs to be minimal. Because there are fewer moving parts, these fans also tend to have a longer lifespan. They're especially beneficial in HVAC systems where reliability is crucial. Belt drive fan. Belt drive fans offer greater flexibility because the belt allows for speed adjustments that can be tailored to specific needs. However, these fans are susceptible to belt wear, which can lead to slippage and energy loss. Routine checks on belt tension and alignment are necessary to maintain efficiency and prevent breakdowns. While they require more maintenance than direct drive fans, they're valuable for systems where precise speed control is needed. Properly maintained, belt-driven fans can balance flexibility and performance. Direct drive fan vs. Belt drive fan. Direct drive fan. The motor is directly connected to the fan blades. Less moving parts which lead to less maintenance. More efficient and quieter than belt drive fans. Belt drive fan. The motor is connected to the fan blades through a belt system. More moving parts which lead to higher maintenance requirements. Can be more powerful than direct drive fans. Multi-speed motor. Multi-speed motors allow fans to operate at various speeds, adjusting airflow to match the system's requirements. This flexibility is especially valuable in applications with variable loads, where full-speed operation isn't always necessary. By using different speed settings, multi-speed motors help reduce energy use during lower demand periods. Implementing these in fan systems allows for targeted efficiency gains and can extend motor life. With the right settings, these motors can significantly improve both system performance and energy savings. Adjustable speed drive, ASD. Adjustable speed drives, ASDs, provide precise control over fan motor speed, making them effective for optimizing airflow based on real-time needs. Unlike fixed-speed systems, ASDs adjust fan speed according to load, minimizing wasted energy. They're ideal for setups with fluctuating airflow requirements, as they can ramp up or down as needed. ASDs also help reduce wear and tear on motor components, lowering maintenance costs. Over time, using ASDs can lead to substantial energy and cost savings. Gear drive. Gear drives are used to adjust the speed of fan systems without relying on belts. This configuration is efficient because it reduces friction and energy loss. Proper lubrication of gears is crucial to avoid wear and maintain smooth operation. Gear drives are preferred in applications where precision and durability are necessary, as they offer a reliable way to control speed. Their direct mechanical connection makes them a robust solution for high-performance needs, with lower maintenance compared to belt-driven systems. Airflow straightener. An airflow straightener is a device installed to minimize turbulence in the air as it enters the fan. By straightening the airflow, it reduces resistance, making it easier for the fan to operate efficiently. This device can lead to more consistent airflow and improved fan performance. Airflow straighteners are especially useful in systems where uniform flow is essential for maintaining desired conditions. They are a simple addition that can enhance overall efficiency and reduce the energy required by the fan. Inlet vane. Inlet vanes control the amount of air entering a fan, adjusting airflow to meet specific requirements. By managing intake, inlet vanes allow the fan to operate efficiently at different speeds without oversupplying air. This control feature is especially helpful in systems with variable load demands, as it allows for energy savings without compromising performance. Inlet vanes also reduce noise and wear, as the fan doesn't operate at full speed unnecessarily. They're a practical addition to boost efficiency in many fan setups. Outlet damper. Outlet dampers are used to control the amount of air discharged from the fan. By adjusting these dampers, airflow and pressure can be fine-tuned to match system requirements. This control helps maintain optimal conditions, especially in systems where airflow needs to vary. Outlet dampers can be manually or automatically adjusted, providing flexibility and ease of operation. They also aid in reducing energy costs by ensuring the fan isn't overworking, allowing for smoother and more efficient performance. Fan speed controller. A fan speed controller is a device that adjusts the fan's operating speed to match current airflow demands. By reducing fan speed when demand is low, it cuts down on energy use and helps extend motor life. Speed controllers are highly effective in systems with variable demands, as they allow for precise control without frequent manual adjustments. The energy savings from reduced speed operation make fan speed controllers an efficient choice for modern systems. They're essential for achieving high efficiency in dynamic environments. Controllable pitch blade. Controllable pitch blades adjust the angle of each fan blade, allowing for real-time airflow changes. This feature is particularly useful in environments with fluctuating needs, as blade angles can be modified to match demand. Adjusting blade pitch reduces the need for constant fan speed adjustments, saving energy. Controllable pitch blades are a cost-effective way to enhance efficiency, especially in large-scale systems where precision is crucial. Their adaptability ensures a balance between performance and energy consumption. Inlet box damper. Inlet box dampers are used to control the air entering a fan, helping to manage system pressure. By adjusting the damper, the fan can deliver the exact airflow needed without excess, leading to energy savings. These dampers are ideal in systems that require precise flow adjustments. Inlet box dampers provide flexibility, as they can be adjusted to match real-time airflow demands. They're a practical solution for improving efficiency in both constant and variable flow systems. Damper types. Parallel blades. The blades in the damper open and close parallel to one another. Opposed blades. The blades in the damper open and close in opposing directions. Single blade. A single blade that pivots to control airflow, often used in smaller applications. Multi-blade. Multiple blades that can be adjusted independently for more precise airflow control. Motorized dampers. These dampers use an electric motor to open and close the blades automatically based on control signals. Manual dampers, operated by hand, allowing for direct control over airflow without automation. Variable air volume, VAV, systems. VAV systems are designed to adjust airflow rates based on the demand in specific areas, making them highly energy efficient. By controlling the amount of air distributed, they maintain comfort and reduce energy consumption in HVAC setups. VAV systems are common in modern buildings where variable airflow is essential for comfort and efficiency. The ability to deliver only what's needed prevents overuse and enhances overall system performance. They're a smart solution for dynamic environments with fluctuating airflow needs. Variable pitch blade. A variable pitch blade in fan systems refers to a fan blade design where the angle of the blades can be adjusted during operation. This feature allows the fan to dynamically alter its airflow and pressure characteristics to match varying system demands, making it highly efficient in applications where load conditions change frequently. By adjusting the blade pitch, the fan can maintain optimal performance while minimizing energy consumption, reducing wear on components, and improving overall system efficiency. Variable pitch blades are commonly used in industrial ventilation, power plants, and HVAC systems, offering advantages such as quieter operation, adaptability to system requirements, and enhanced energy savings. Disc throttle. A disc throttle in fan systems is a flow control mechanism used to regulate the airflow by adjusting the size of the flow passage. It consists of a disc or plate that can rotate or slide to partially or fully block the airflow within a duct or system. This throttling action changes the pressure and volume of air delivered by the fan, allowing for precise control over system performance. Disc throttles are commonly used in applications requiring variable airflow, such as ventilation, cooling, and industrial processes. While effective for airflow regulation, throttling can increase energy consumption and pressure losses, making it less efficient compared to methods like variable speed drives. Regular maintenance is crucial to ensure smooth operation and prevent wear or damage to the throttle mechanism. Variable frequency drive, VFD. A variable frequency drive, VFD, in fan systems is an electronic device that controls the speed and torque of the fan's motor by varying the frequency and voltage of the electrical power supplied to it. By adjusting the fan's speed to match system demand, VFDs offer precise control over airflow and energy efficiency. Unlike traditional throttling methods, VFDs reduce energy consumption by slowing down the fan motor instead of mechanically restricting airflow. This results in significant energy savings, particularly in systems where the fan operates below full capacity for extended periods. VFDs also minimize mechanical wear, extend equipment lifespan, and reduce noise levels. They are widely used in HVAC systems, industrial ventilation, and cooling applications, ensuring optimal performance and lower operational costs. Energy consumption calculator. The image shows two digital meters. The meter on the left shows a reading of 238.54 V, which is likely voltage, 1.6474 which is likely amperes, and 0.998 an unknown unit. The meter on the right shows readings of 59.624 K, which is likely kilowatts, 40.374 K, which is likely kilowatts, and 0.8284 K, which is likely kilowatts. Heat exchanger. A heat exchanger in fan systems is a device that facilitates the transfer of heat between two mediums such as air, water, or refrigerants without mixing them. In fan systems, heat exchangers are commonly used to condition air by heating or cooling it before it is distributed through ventilation ducts. For example, in HVAC systems, a fan pushes air over a heat exchanger coil containing hot or cold fluid, allowing the air to absorb or release heat. Heat exchangers improve energy efficiency by recovering waste heat in industrial processes or maintaining desired indoor temperatures in buildings. Types of heat exchangers in fan systems include plate, coil, and rotary types, each suited to specific applications. Proper maintenance is crucial to prevent fouling, which can reduce heat transfer efficiency and increase energy consumption. Filters. Filters in fan systems are essential components designed to remove dust, debris, and other contaminants from the air before it enters or exits the system. These filters help maintain indoor air quality, protect the fan and associated equipment from damage caused by particulate buildup, and improve overall system efficiency. Common types of filters include panel filters, pleated filters, HEPA filters, for high-efficiency particulate air filtration, and electrostatic filters. Belt drives. Belt drives in fan systems are a mechanical method used to transfer power from the motor to the fan. They consist of a belt looped around pulleys, one connected to the motor and the other to the fan shaft, enabling the motor to drive the fan at the desired speed. Belt drives are popular in fan systems because they provide flexibility in speed adjustment by using pulleys of different sizes to achieve variable speed ratios without changing the motor's operating speed. Worn bearings. Worn bearings in fan systems are a common issue that can significantly affect performance, efficiency, and reliability. Bearings support the fan shaft, enabling smooth and low-friction rotation. Over time, bearings can wear out due to factors such as misalignment, improper lubrication, excessive vibration, or prolonged operation under high loads. Symptoms of worn bearings include unusual noise, example grinding or humming, increased vibration, reduced fan efficiency, overheating, and, in severe cases, fan failure. Motor. The motor in fan systems is the primary component responsible for driving the fan to create airflow. It converts electrical energy into mechanical energy, powering the fan blades to move air for ventilation, cooling, or heating purposes. Motors used in fan systems are typically electric and can vary in type, such as induction motors, synchronous motors, or brushless DC motors, depending on the application and efficiency requirements. Air duct. The air duct in fan systems is a crucial component that facilitates the transportation of air between the fan and different areas of a building or system. Ducts are typically made of materials such as galvanized steel, aluminum, or flexible composites and are designed to minimize air resistance and ensure efficient airflow. In HVAC systems, air ducts distribute conditioned air, heated, cooled, or ventilated, to maintain indoor comfort and air quality. Impeller. The impeller in fan systems is the rotating component responsible for moving air or gas by converting mechanical energy from the motor into kinetic energy. It consists of blades or vanes arranged around a central hub, designed to generate airflow and pressure as it spins. Impellers come in various designs, including centrifugal, axial, and mixed flow, each suited to specific applications based on airflow and pressure requirements. Thank you for your attention. For more details, please contact TSD Office Engineering GHG. We appreciate your interest in ESG initiatives.